So we have another example. This time we have 3 blocks of some sort. They're connected by a wire over a massless frictionless pulley. Now at this point, the purpose of the massless frictionless pulley is to allow that wire connecting the mass to essentially slide over it. We're not going to worry about the forces involved in causing the pulley to rotate. We'll look at rotational motion in chapter 12, so we'll get there. Ultimately, we want to find how much mass is here on the left side. It's not quite as straightforward to find an overall equation for the system as a whole when we have different directions going on. As we look at this picture, they are telling us the tension in the cable attaching those 2 masses together. Now, we do not want to assume this system stays stationary. We need to determine if that is going to be the case. So not assume. There has to be something about the problem that tells us that the system would stay stationary. I do know that the net force on any one of these individually, any one of these blocks, will equal the mass of the block times its acceleration. So we can start looking at the net force on them individually. Since I'm given this tension of 133 newtons, I'm actually going to start with this 10 kilogram mass. Because if I know its mass, I can determine the force of gravity acting on it. And then I know the tension, and so I know some forces, and that will allow me, hopefully, to calculate for acceleration. So symbolically, this mass 1 represents my 10 kilogram block. I know there is tension pulling upwards. I know this value. I know there's a force of gravity downwards. So if I write out the equation that describes these forces in the y direction, I can say that tension 1 pulling upwards minus the force of gravity pulling downwards needs to equal mass times acceleration. We know the tension is 133 newtons pulling upwards on that block. That was given in the problem. The mass is 10 kilograms. G we know is 9.8. So we actually find out here that there is an acceleration. The value I'm getting is 3.5. The fact that I'm getting a positive answer means this block is going to have an upward acceleration of 3.5 meters per second squared. But this block is connected to the 15 kilogram block, so the 15 kilogram block is going to have an acceleration upwards of 3.5. This is connected all the way around to the block hanging on the left, which means this block on the left needs to be accelerating downwards with that acceleration of 3.5. So the 3.5 is the magnitude. We need to account for the direction when we set up the forces for these individual blocks. So I know the block on the left and the block on the right. The tension here on the left that's pulling up on this block is also pulling up on this block. That's also a consequence of this massless frictionless pulley. It allows for the tension in the wire connecting all the way around to be the same. So ultimately, we're trying to get and figure out the mass of this block on the left. So on the left block, I know there is this tension 2, which we don't know the value yet. That tension is acting upwards. The force of gravity on this block is acting downwards. And we do know there is a downward acceleration of 3.5 meters per second squared. When we write out net force equals ma for this block, we have tension 2 upwards, we have mg downwards. This has to equal mass times, we're going to need to put a negative sign on this acceleration to account for it being downwards. But we still have 2 unknowns here. We don't know tension 2, nor do we know the mass. So we don't have enough information yet to solve this particular equation, which means we need to go back and look at this 15 kilogram block. So the 15 kilogram block, I'm going to call this M2 in terms of writing out the equation symbolically. This block is experiencing the force of tension 2 upwards. So again, the tension 2 is all the way connecting the block M to the 15 kilogram block. The 15 kilogram block is feeling that tension pulling upwards. There's going to be a force of gravity downwards because it has mass. But there's also going to be a force of tension 1. This 133 newtons downwards. So this 15 kilogram block has 2 separate wires connected to it. And so it is experiencing 2 different tension forces. Now, to relate these forces to the acceleration the block experiences, we need to look at Newton's second law. So net force is mass times acceleration. From our free body diagram, we know that tension 2 pulls upwards, tension 1 pulls downwards, force of gravity pulls downwards. So this here represents the net force on this block in the y direction. So that needs to equal the mass times acceleration. We've already calculated the acceleration. If the 10 kilogram block is accelerating upwards at 3.5 meters per second squared, then the 15 kilogram block is also accelerating upwards with that same magnitude. T1 was given in the problem. So ultimately, our only unknown at this step is this T2. We know T1, the tension between the 15 and the 10. We know the mass, so we can find the force of gravity. We've already calculated the acceleration, so we can solve for this tension T2. I'm getting 332.5, which will be in newtons. Now that we know this tension, we can come back to the left block and solve for the mass. So we know the left block is feeling that pull upwards of that tension 2 that we just calculated. There's a pull of gravity downwards. And then mass, the acceleration, again, the reason we need to put the negative sign in here on the acceleration is because it's accelerating down. We have to account for the direction of that acceleration. So we end up with two of the terms. If I bring that to the other side, I can factor it out and then solve for the value of m. So let's see, we have three significant figures. So 52.8 kilograms is what this would need to be. So ultimately that means the mass on the left, in order for the tension on the right in that particular wire to be 133 newtons, this mass on the left needs to be 52.8 kilograms.